What is up, ladies and gentlemen? We are going to unpack Newton's Law of Gravitation, which is often just NOLG. So with Newton's Law of Gravitation, we denote a couple of things. So the first thing that Newton found out, he said that the force due to gravity is proportional to the masses of your two objects. He said if one mass increases, gravitational force increases. Another thing he noticed was that the gravitational force is proportional to the inverse squared of the distances between the center of the objects, not the surface. So what I mean by that, if we look at two objects and we're trying to determine their distances between, you go from the center of those objects, not the surface. So if I do the same two objects here, this is not the way to do it. It's from the center. Cool. So when you look at an object like Earth rotating around, an object rotating around the Earth, you take the radius of the Earth plus the distance it is away from the Earth. Very often they like to trick you on that kind of stuff. And so with this, Newton came up with this gravitational constant called G, and that's 6.7 times 10 to the negative 11th. And I actually don't have those units on me. There's something funky. Anyways, so let's go ahead and just look at the whole formula all together. So the gravitational force of an object is G(m)m over r squared. One thing I forgot to mention, this is a direct relationship, and then this is an inverse squared. So let's do that in a different color so we don't get confused. This one right here is an inverse squared. So as one thing goes up, the other thing goes down, but it's also a squared relationship. So it's a good kind of litmus test to see if you're understanding those relationships. If I double one of my masses over here, what happens to my force? It doubles. If I double the distance between two objects, what happens to the force over here? It cuts in quarter. Now, if you don't understand those relationships and how to manipulate, I'm not going to cover it in this video, but you're welcome to ask me sometime later. So let's go ahead and keep moving forward. So what can I do with Newton's Law of Gravitation? So when an object is in motion or in orbit, so satellite in orbit, what do we then are we able to say? Well, we're able to say then that our centripetal force is then equal to our gravitational force only. And back in that previous video, we said centripetal force is mv squared over r, and that's equal to G(m)m over r squared. So with this, I'm able to do a couple of interesting things and to note what's going on. First thing is that the mass of the satellites cancel out. So when you're looking at the orbital speed of a satellite staying in motion, it's not really determined by the actual mass of the satellite. It's determined by the mass of the planet and how far away it is. So if you double the mass of a satellite, it does nothing to the speed, it does nothing to the period, and things like that. Another thing I want to just kind of unpack, but I never really think it'll show up on a test, but it's just good to know, is we know the lowercase g as 9.8 meters per second squared, but in this class we often just say 10 for easy math. So where does this come from? And we can actually unpack this saying, if we look at the force due to gravity, which we've covered earlier as mass times gravity, and we now also have that as G(m)m over r squared, we notice something interesting. If we cancel out the masses here, we get a formula for the gravity of any planetary body. And all you need to know is the gravitational constant, which is constant, the mass of that planet, notice I use a capital M here, and the radius of it squared. Now, if you plugged in the mass of Earth and the radius of Earth squared, on average, you'll get the gravity here to be pretty close to 10. It'll change based off where you're at. If you're above sea level, below sea level, things like that. But overall, it's going to be pretty close to 10. All right, moving on forward. What we're able to say here is, I'm just going to write this down. I've already talked about some of this. So velocity, mass of planet, and radius have relationships. What doesn't have a relationship is mass of satellite. Has no relation. And that's I think all I'm going to unpack when it comes to those. Newton's law of gravitation really doesn't show up for too many different types of questions. Usually what you have to start off with is, is it in orbit? If it is, you're 99% of the time. I can't think of another reason of starting somewhere else other than here. You then expand it down to here, and then you solve for whatever you're trying to solve for. But that's kind of it when it comes to Newton's law of gravitation, as far as this class is concerned. Now let's talk about Kepler's laws. Now Kepler's laws are, I guess that's 1p, isn't it? Kepler's. At least I got it written down as 1p. Might be 2. Anyways, moving on. Kepler's laws are Kepler came by and expanded on Newton's laws of gravitation using some of the calculus that Newton figured out. If you want to thank anybody for calculus, Newton discovered calculus so he could do physics better. So the first of Kepler's laws is that all planetary bodies follow an elliptical orbit. With the sun at a focus. So if we look at a planetary body, like let's look at the Earth going around the sun. There we go. Try to do the best I can. If you look at the Earth, let's do blue for the Earth because the Earth is mostly water. Oh, I just erased my elliptical orbit. Let's put that back in there. And then if you didn't know that, I'm sorry. Also, if you didn't know that the Earth orbits the sun in an elliptical way, not necessarily in a circular way, I'm also sorry about that. So the sun itself is often drawn as the center of the orbit. It's actually at one of the focus of an ellipse. So every ellipse has two focus. The sun, or the star of that orbit, will be at one of the focus. That's Kepler's first law. With that, Kepler went off to do some calculus. Now, you don't necessarily need to understand the calculus portion of it, but this is just kind of some things nice and neat to tuck in your back pocket. And so Kepler's second law, it says that there is, so the area covered, there we go. Area covered for a certain period is constant. Now, you can't explain this mathematically without using calculus, so I'm not going to use the calculus to explain it, but here's what we say overall. If I were to take my elliptical orbit and I were to denote that a planetary body is moving from here to here versus here to here, there we go. And this time interval right here is the same amount of time. So if this was Earth's orbit, let's call it, a month. If that time period is the same, then the area covered is the same. So if T1 equals T2, the area covered by 1 equals the area covered by 2. So this area right here is area 1. This area covered right here is area 2. So other than that, just kind of nice thing to tuck in your back pocket is every once in a while we'll see planetary motion questions pop up, but they are very infrequent. So I wouldn't put too much stock into this, but we are technically covering everything. And then the last one that pops up is Kepler's third law. And that is, that's the law of periods. And that's where the period of A, or period of 1 squared, this is of 2 different objects. So let me draw a picture and I'll explain it here in a second. There we go. So the period of object A around a body is proportional to this formula, period squared over radius cubed, saying that if I have an object A where it takes object A a certain amount of time to go around that planetary body, since the second object, let's call this A, let's call this one out here B, if it takes object B a certain amount of time to go around, there is a relationship to object A, and that just follows this little law of periods right here. So if you know the period of one planet, the radius of that planet, and the period of the other planet, you can predict how far it is away from that planetary body. Now, let's go ahead and elaborate just a little more using some color. How about that? So this would be the radius of A. This would be the radius of B. And last one bit, this would be the orbital path of A. And then this would be the orbital path of B. Alrighty guys, I believe that's going to be it as far as Kepler's laws. I'm going to tag in one last thing of looking at gravitational potential energy and why that formula looks a little funky. So, gravitational potential energy, if you look at your reference sheet, looks like this. U sub G equals negative capital G mm over R. Now this is talking about potential energy of a planetary body. This is not potential energy of something close to Earth. So of that planetary body in orbit, how do you calculate the potential energy? The reason that we even look at this stuff is if you think about a planet going around an orbit, it's going to kind of have a slingshot effect. So as it comes closer to the end that has the closer focus to the star, this is when it's be going the fastest. So the kinetic energy is going to be the highest. Because of that, as it goes away, that kinetic energy is going to be the lowest. So it's going to be going the slowest energy, or the slowest rate, the further away it is. So with that, we then say that its potential energy is at a lowest when it's closest, and its gravitational potential energy is the highest when it's further away. Now, if we look at the reference to this formula right here, the reason this is a negative is because what we've typically denoted as when things go further away, we want their gravitational energy to increase. And so by plugging in this negative right here, when it goes further away, it becomes less negative. So since it becomes less negative, it's still technically increasing. As far as it comes to the glass, we're not really too concerned on where to get this formula from. It's just more of a plug and chug, and then you're kind of good to go. When it comes to planetary stuff on the AP test, I'm really not too concerned, and it pops up a very small portion, but we've officially wrapped up this unit. All right, you guys got any questions, let me know.